If we pick a random star in our galaxy and observe it through a telescope, how can we measure its speed relative to the Earth? Well, first, we must realise that all stars will emit a spectrum of light. Now, the light from the star might look slightly more red or slightly more blue in colour, but its light can be split up into a rainbow of different colours using a prism. When we analyse a star's light, this continuous spectrum will be crossed with a series of black lines or dark lines. This is where atoms of gas have absorbed a certain frequency of light from this white light, and the light that's received with our telescope is the remaining light from the star. So this is known as an absorption spectrum. Each star will be surrounded by a low pressure gas of mainly hydrogen, and as the light from the star passes this gas, the gas molecules will absorb certain frequencies of light. So with hydrogen, we get an absorption spectrum that looks like this. And we can also get this result in a lab by shining some white light through some hydrogen gas. However, something strange happens to an absorption spectrum when we receive this light from a distant star. We find that these black lines have either been shifted to the red end of the spectrum or to the blue end of the spectrum, depending on how fast the star is moving away from the Earth or towards the Earth. So this absorption spectrum has either red shifted or blue shifted. So when light from a star has been red shifted, this means that its light has increased in wavelength by some fixed amount. If it's been blue shifted, the wavelengths of this light from this star have got smaller. So how can we use this information to measure how fast the star is moving relative to the Earth? So we can use a principle known as the Doppler effect, and I've covered this in a previous lesson for sound waves, and I'll put a link in the card in the corner here if you want to watch that. So the equation to measure this Doppler shift for electromagnetic radiation is written like this, where we have the shift in wavelength, the change in wavelength, divided by the wavelength of one of these black bands here for a certain type of gas in a lab, normally hydrogen. And this is roughly equal to the change in frequency by the frequency of light from the lab, which is approximated to the velocity of the object, so a star in this case, divided by the speed of light. Now, we only use an equal sign when this velocity term here is much smaller than the speed of light. If it's comparable to the speed of light, so if we've got an object within the universe that is moving at a certain percentage of the speed of light, say 10% of the speed of light, then we're going to need to take into account relativistic effects and include some of Einstein's work into this problem here. But for objects moving at much smaller speeds than the speed of light, say for example hundreds of kilometers per second, then we can use this formula. So we've got an absorption spectrum from a star as the light is passing through hydrogen gas, and we've got this on the top band here, and at the bottom we've got white light going through hydrogen gas in the lab. And you can see there's a slight shift in these bands. So the difference in wavelength is equal to the wavelength of one of these bands here from the star minus the wavelength of the same band from the lab. So let's do a quick practice problem. We obtain the hydrogen spectrum of light from a star named Ursa Majoris. One of the wavelengths of this hydrogen spectrum is measured to be 486.112 nanometers. But the same spectral line under lab conditions is found to be slightly larger, with a wavelength of 486.133 nanometers. So I've written this out as the wavelength for the star, the corresponding wavelength we'll get in the lab, and we need to find the the velocity of this star relative to the Earth. So the hydrogen spectrum has shifted to the blue end. This means that the star is moving towards the Earth. So delta lambda divided by the delta lab, which is equal to the velocity divided by the speed of light. Rearranging this equation, we get the velocity is equal to the speed of light multiplied by the wavelength from the star, or the spectral line from the star, minus the wavelength of the spectral line, the equivalent spectral line from the lab, divided by the wavelength of this spectral line from the lab. And remember here, the wavelengths that we're using are represented in nanometers, which is a billionth of a meter. And we need to use the equivalent meter term here. So our values are at 10 to the minus 7 meters here. Our velocity on our calculator is 12,959.416 and so on. But because our smallest value here, which is the value for the speed of light, is only accurate to two significant figures, then our final answer can only be accurate to two significant figures. So I get an answer of negative 1.3 times 10 to the 4 meters per second. Now the negative sign means that the object is moving towards us at 13 kilometers per second. Now it's really important to realize here that this value is the velocity along the direction of sight. We've got the Earth on the right hand side. This dotted line here is the direction of sight, so this is where our telescope is pointing in, and it's pointing in the direction of this star here. Now along the direction of sight is our velocity, so this is how quickly the star is moving towards the Earth, which is at 13 kilometers per second. But the star might not be moving directly towards us along this direction of sight. It might be moving at a certain angle. But if we view this star in our telescope and we track it over months or years, we can see how fast it's moving in the horizontal direction. And then we can use trigonometry to find the actual velocity of the star along its direction of motion.